Okay, so figure 7 represents momentum time graph for an object of mass 2 kilograms. Okay, so I've already displayed the answer there. It's C. It's out there, guys. Let's derive it. Why it's C. So F is the time rate of change of momentum. That's Newton's second law. So for this part where we're accelerating, all right, change in momentum would be, this is 0 here all the way to 400. So you have 400 minus 0 divided by change in time, 10 minus 0. So you have 400 over 10. So our accelerating force there is force in Newton. So we can get the acceleration, which is force over mass, which gives us 20 meters per second. We can come over here and then talk about the force when the particle is now decelerating. Okay, so the magnitude of this, or the force, the decelerating force, is changing momentum again. So again, you are moving from 400 to 0 now, so the change is negative, and the change in time will be 23 minus 18. Okay, so we have final the momentum or the force generated when you are decelerating. The decelerating force is negative 18 newtons. So take note that the magnitude of the accelerating force is half the magnitude of the decelerating force, and clearly that's what 1 is saying. So that's statement 1 right there. So the acceleration, you can go over and get the acceleration, but the area under this graph, guys, the area under this graph, this a trapezium, so half sum of our sides times height. That's how I get the area, easy. So that's 6,200 kilogram meter. So the significance of the area under this graph would basically be the unit here multiplied by the unit here. Okay, so the unit here is the Newton second, which is kilogram meters per second, multiplied by the second, so you have just kilogram meter. Okay, so if I get this, if I want to get the displacement that the particle covers in all this journey, I'll simply need to get this area divided by the mass. Okay, because if I get this area now divided by the mass, it gives me the displacement. So if you do that, you have 3,100 meters. So that is the total displacement of the particle. So this statement 2 here is wrong. Statement 3 says the area on the graph represents the work. Of course not. This area is kilogram meter. That's no unit for the work. So 1 only is the right answer. So our answer is C. Which of the following statements is or are true? A homogeneous equation must be correct. Of course not. So 1 is wrong, right? Homogeneity is a necessary condition for correctness and not a sufficient condition. So whenever an equation is homogeneous, it does not mean that it's correct. Statement 2 says a homogeneous equation can be wrong because it contains a unitless constant. Correct. Okay, so one of the reasons why a homogeneous equation is not always correct is because the equation might contain unitless constant, and homogeneity does not test for the presence of unitless constant. Okay, so yes, it can be homogeneous but then wrong because of the presence of that. So 2 is correct. Statement 3 says a correct equation must be homogeneous. Correct. If homogeneity is a necessary condition for the correctness of a physical equation, then the correctness of a physical equation becomes a sufficient condition for the homogeneity of a physical equation. So whenever an equation is correct, the equation must be homogeneous. So 2 and 3 are correct. So our answer is B. So resistors of resistances that connected in series and later connected in parallel. All right, so let's do the series. When they're in series, what's our combined resistance? 26 ohm, right? 12 plus 8 plus 6. Now when can we get the conductance? The conductance is basically 1 over resistance. So in this particular connection where they're in series, the conductance therefore becomes 1 over 26, which gives us 38 millisiemens. All right, so this is not seconds, this is Siemens. So conductance is measured in Siemens. So we can go over and then find the total resistance when they are connected now in parallel. All right, so when they are connected in parallel, 1 over R total will be 1 over R1 plus 1 over R2 plus 1 over R3. So we can make RP our subject, and 1 over RP already, this is 1 over RP already gives you the conductance. So when you calculate this, that's already the conductance. So it gives you 0.38 Siemens. So our answer is B, because B says 2 says combined conductance of the series connection is 38 millisiemens. Correct. Combined conductance of the parallel connection is 0.38 Siemens. Correct. Right? Boom. A particle oscillates with simple harmonic motion of amplitude 5 cm and a maximum speed of 25 centimeters per second. Okay, let's do some work here. So Vmax, of course, is omega r. So our omega is going to be Vmax over r. Our Vmax is 25. Our r is 5 centimeters. So our omega is going to be 5 rads per second, right? That's easy, right? Now, but omega is 2 pi over t. We're going to come here and make t the subject. T is 2 pi over omega. That tells us that, well, our t is 2 pi, omega is 5 over 5, so it gives us t as 1.3 seconds. Now let's come over here and then get A max. Our A max is V squared over R for a particle oscillating in simple harmonic motion. So our A max is, our V here was 25 centimeters per second, so we're going to get 25 squared there over 5. Remember that this is centimeters. So we're going to get A max as 125 centimeters per second squared. So we have to convert from centimeters to meters. So we have to do what? We have to multiply by 10 to the negative 2. So that gives us 1.25 times 10 to the 1.25 meters per second squared. So our maximum acceleration is that. So our answer is A, because period is 1.3 seconds. Particles maximum acceleration is 1.2 meters per second squared. But this is 1.25. According to the accuracies of physics, clearly B number statement 2 is wrong, right? Because the approximation of 1.25 is not 1.2, that's 1.3. So yeah, so I'm just really going with A because the examiner that I discussed with also went with A. So we'll leave it at that. All right, but if I was in the exam hall, swears I would have picked one only, which is C. Doppler's effect occurs. All right, so first off, you need to know what is Doppler effect. Doppler effect is the apparent change in the frequency of sound observed by an observer as a result of relative motion between the source and the observer. Okay, so you've seen me talked about it a little bit here. That's the definition. But come over here, this is where the intricacy lies. When two bodies move at the same speed in the same direction, they are at identical positions from each other at all times. Hence, there's no relative motion between them. Hence, 2 is not absolutely true. All right, so you really need that for relative motion to be between two objects when they're moving. They need to be the distance between them, or the displacement vector that links that describes the distance between them has to be changing with time. All right, if it's not, then of course there's no relative motion between them. You don't observe Doppler effect there. All right, so statement 2 says only when both source and observer move. Both source and observer can be moving in the same direction with the same speed. You're not going to observe Doppler effect in that case. All right, statement 1 says only when the source moves. That's not true. All right, because, well, the source can be stationary but the observer is moving, so you are still going to get relative motion between the source and the observer, and then Doppler effect. So statement 1 and 2 are not true. Statement 3 is our best answer, so our answer here is D. In the alpha particle scattering experiment, which of the following deductions Y corresponds to the observations in X? Okay, so statement 1, most of the alpha particles pass through undeflected. Correct. Most of the atom is empty space. Correct. Okay, the observation and the deduction correct. So the deduction correct. Statement 2, a few of the alpha particles were deflected through small angles. The positively charged nucleus is located at the center and is small. Well, that's off, right? So statement 3 says very few of the alpha particles were deflected through large angles. Correct. The nucleus is positively charged. No, the nucleus is very dense. That's the correct deduction from that. All right, so very large angles tells you that, well, it's positively charged, and then very dense. Okay, because the alpha particles themselves are very massive, so if they are hitting an obstacle and then they are getting deviated through large angles, that obstacle has to be very massive itself. So the nucleus is small and massive, so it talks about the density. Correct deduction there. So our answer there is C, one only. Okay guys, now we go into the most important part of physics, which is graphical analysis. Physics paper 1, I must add. So the reciprocal of the distance from an object to a camera, the reciprocal of the distance from the lens to the film. Let's talk about this a little bit. Object camera distance is U. All right, the film is where the image is formed. I just need to make that clear. So the lens film distance is V, which is your image distance. Using the lens formula, 1 over F equals 1 over U plus 1 over V. So we make 1 over U the subject, so you are going to notice that, well, Y here, which is the reciprocal of the object distance, is negative reciprocal of the image distance plus C. So that tells you that this is a straight line graph whose slope is negative. Intercept in the y-axis positive. So you would need this guy to be falling like this, but not through the origin and not through this quadrant, but through the first quadrant. Okay, so the answer should have been A, but not drawn like this. So A falling through this first quadrant, all right, and the intercept somewhere up here. Correct, that would have been the right answer. And then the right answer could have been C if you had, if this guy was rather falling. all right, not rising but falling. Or this guy, if this guy was not rising but falling. So all the graphs had an issue. So your answer here is, so this is actually the actual graph we have drawn, and the answer here should have been A. Again, I've explained why this one is really not the answer, because the good answer here should have been A. This guy has a negative slope, and this is the only guy who has a negative constant slope. This guy has a negative slope, but it's changing with time. So this guy is off. So this is the only guy who has a negative slope, but the intercept should not be 0. 1 over f, the reciprocal of the focal length of the lens, is not 0. So this guy has to come from up here, and then it's falling all the way. All right, so you make, I'm sure that one is clear. Okay. The gravitational field intensity, the distance from the surface of the earth. All right, this is one of those questions too that had a problem. Let's just do the maths. Gravitational field intensity, you have gm over r squared. All right, so of course that's field intensity from the surface. So you notice that y is 1 over x squared. So this is basically a graph of y equals 1 over x squared, because gm is a constant. All right, so now notice that x cannot be 0, which implies that x equals 0 is a vertical asymptote. Notice also that the limit as x tends to infinity of this expression like this, or as r tends to infinity of all of this g, basically gives you 0, which tells you that the line y equals 0 at the x-axis is a horizontal asymptote. Hence the graph is D, which is not really D, because again you notice that this line x equals 0, which is the y-axis, is supposed to be a vertical asymptote, but D is touching this guy. Can you see that D is touching it? So the problem here, we discussed this problem with the examiners, is that this guy is supposed to come up here but not touch this y-axis. All right, it's not supposed to touch that y-axis. So this is actually how the graph looks like. So this is a graph of y equals 1 over x squared. So you have the y and the x-axis as asymptotes, and then you have the graphs not touching the x and y-axis like that. And that's why from the center of the earth you would have a straight line like this. Let me see if I can draw that. You would have a straight line if you were supposed to draw field intensity from the center of the earth. So notice that this is from the surface of the earth. From the center of the earth you would have a straight line like this. Oh, don't mind that line, it's terrible, but I'm just saying that there's a straight line from this origin all the way to that surface, and then now from the surface it begins to fall in this inverse square manner. Okay, so you have a straight line like that all the way to that surface, and it begins to fall in this inverse square manner. Perfect. Telling you that from the surface it falls like that without touching this y-axis. So our answer here is that. So you have refractive index of the glass prism, reciprocal of speed of light. Oh, this one was a typical mess again. So you had 3 messes on this graphical problems in the Southwest mock. Refractive index of glass prism, that's a constant. Reciprocal of speed of light, that's a constant. So you're plotting a constant versus a constant. Like there's really no point. It's like someone asks you to sketch the graph 2 equals 3. It makes no sense. Like if you think about that, that makes no sense, right? Perfect. So yeah, there's no sense with this one, but I've done a little bit of work that just brings out some sense. Refractive index is speed in air divided by speed in the medium. Now refractive index, so we'll put 1 over speed of the medium out there, then dot. Now this c here we can write it as 1 over 1 over c, because this c can go up back up there, right? So I just want to do some crazy things here. So refractive index is 1 over cm, then dot 1 over 1 over c, right? No problem there. Now if this is our slope and then we're plotting a graph of the reciprocal of the speed in air, reciprocal of speed of light, okay, so you notice that that becomes our x. But now as you're changing media, this guy is also changing, and then this guy is also changing, so everything is basically changing. So there's really no relationship here, but like I was just trying to bring up something. So you notice that, well, you could have this kind of relationship if you're just talking about a particular refractive index of a particular medium, and then reciprocal of the speed of that medium is a constant, and then there you get reciprocal of speed in air. So yeah, these are just some crazy things I decided to do with little maths, but again clearly you see that the question is wrong, right? I'm just doing nasty things there. All right, so again you notice that I'm just saying B. This is an unanimated answer, so it's not the right answer. It's just like I forgot to animate that. All right, potential energy of a body executing simple harmonic motion. Okay, time. Let's do some good work here. Now PE is half kx squared. Okay, for in simple harmonic motion our k is m omega squared and our x is r sine omega t. So our p is going to be what? Half. In place of k we're going to put m omega squared. In place of x squared, we're going to put r squared sine squared omega t. Okay, so respect to time, you notice that our PE is going to start from rest. Okay, so from the origin like this, and then the guy is going to be increasing over time. So because this guy is maximum when all of this thing is 90 degrees, so at t equals 0, our guy is minimum, PE is minimum at t equals 0. Okay, why ke is rather maximum, but let's get ke and see what happens. So ke is half mv squared. So how do I get v? I simply come and differentiate this displacement expression. If I differentiate this, I'm going to have differentiate this sine function, I'm going to have omega r cos omega t. So we'll put omega r cos omega t here, and then we square that, and then we simplify. You notice that our k is half m omega squared r squared cos squared omega t. At t equals 0, cos is 1, so you notice that our k is maximum instead. So k would start from a maximum point like that and then oscillate downwards. Notice that they are sinusoidal, right? These are oscillatory functions, so they'll be oscillating like this, but ke would be starting from maximum, while pe is 0 from at t equals 0. Are we together? So you notice that our mechanical energy will be pe plus ke, and then when you add these two guys together, you'd have factor out half m omega squared r squared, half m omega squared r squared. Then you have sine squared omega t plus cos squared omega t, which gives you 1, and so you are left with half m omega squared r squared. So our me there will be a constant. So if you were to plot mechanical energy for a particle that is oscillating in simple harmonic motion with time, this would have been the answer, d would have been the answer. But now you're talking about pe, so c makes sense to be the answer because it's 0 at the origin. All right, so this guy is 0 at the origin, but it's not oscillatory, so it's not like c is really the ideal answer because this guy is supposed to be oscillatory, so it's supposed to go like this, like that, not like that. So again, c is really not the best answer. To swears, I don't know why there are so many errors in this thing. So this is how this thing is supposed to go. It's supposed to come from here and then oscillate like this, oscillate like that, oscillate like that, and so on and so forth, right? Why ke rather starts from here and then oscillates like this, and then oscillates like that, and then oscillates. So yeah, you get the point. So again, that thing is off, so our answer is just C, based because I mean, like, is the next best answer. All right. Root mean square speed of gas particles, density of a fixed mass of gas at constant pressure. All right, so let's do the maths. Oh, I've not demonstrated this, but I've solved this problem in the paper 2. All right, so please check out, make sure you check out the root mean square speed of a gas particles and then density of a fixed mass of gas. So make sure you check that paper 2. I've solved it, I've demonstrated it, because the root mean square speed is of course the square root of 3 times the pressure divided by the density. All right, so there's some sort of inverse relationship going on there, so you clearly see that this is the relationship there. But again, please make sure you check out the paper 2 of the physics. All right, thank you guys so much for watching. Thank you for subscribing. If you have not yet subscribed, please subscribe, hit the notification bell so that you don't miss any uploads from our channel. Please share our content, like, comment. Those things help us a lot and help YouTube push our content to other viewers. Thank you so much. Keep loving physics.